Oh, okay. Okay, somebody, you want to sit there and or somebody and maneuver with that. It doesn't catch all the, catches 4 blackboards instead of 6. Okay. All right. So far what we've done so far? So far is right, Polish groups, what's the definition, and then division according to the type of metric on the group. And we had a lot of examples. These are important because they illustrate these groups, Polish groups that are not locally compact, they really are in various areas, show up naturally in various areas of mathematics. But we also did some interesting, for example, some groups that are really interesting in their own right, like Grajek's group, with lots of free groups inside. Okay, so today I want to talk about the universal, an example of a universal Polish group. So that's a group, so it's not unique, but it's a group, it's a Polish group with the property that every Polish group is a closed subgroup of that single one. Yeah? So this is a result of Uspensky. But before we do that, we'll do the Urson universal. Let's just call it Urson universal space. And then the group that will be important is the isometric group. The group here is the isometric group of this Urson universal space. And we know that the universal space will be Polish metric space. So the isometric group will be, with the usual topology, as we introduced last time, is a Polish group, that we know. And then we'll just see how everything else, how every other group embeds. So there are various people through this development. So of course, this actually, so we started, of course, by Urson. This is very old. The construction is from the paper in 27. Urson was posthumous. He died in 24, and everybody knows about it, the swimming accident in Normandy or Brittany, somewhere in France in 24. It was published in 27 by, it was edited by Alexandrov, or published. Urson was the author of the paper. So Urson, and then the development was Akletov. And Uspensky. So this is like the 80s, and this is maybe 90s. So what's this space? The definition. Is so a metric space. There is a metric space. So with a metric space is called universal space. If it is separable, complete, and it has the following property. Okay. For all finite metric spaces, X subset of Y. I should call it something. Urson universal space U, finite metric spaces, and an isometric embedding. or I should say each isometric embedding. Each isometric from X U extends to an isometric embedding. From Y. So these are finite. So they're both, Y is finite, X is a subspace. And I have an embedding, X is essentially a subspace of U as a metric space. And then I can extend it to this bigger finite space, yes? Is this definition clear? No. Some words need to be universal. So Urison, I explained, he came up with this, but there is still, we have to explain why is this universal. So let's make a remark that makes checking this condition easier. I mean, an obvious remark. So it's enough to show, note, it suffices to check star for Y equal X union X star for spaces of the core spaces. Right, so Y is X plus one more point. And this is obvious, right? Because if I have a bigger Y that's finite, Y is finite. So finitely many points outside of X, I just enumerate these points. X is already embedded in U. I then embed the first point. Now this bigger space is embedded. I embedded the next point and the next point and the next point, right? So it's enough to, it will be just convenient in practice to keep this in mind. Yeah. Then, okay. Then the second argument here one wants to run is it's universal with respect to all separable metric spaces. So each separable metric space embeds isometrically into U. Yeah. And okay, so how do we do it? Let me I'll just draw some pictures. Because this is saying the same argument would come up several times. So, so if I have, let's say, that okay, I will use these letters X be a separable metric space, X D be a separable metric space. There is, so this is proposition. There is an isometric embedding. From X with D into U. So U has, when I write U boldface, I mean it's with that metric. It's not topological space, it's a metric space. Okay. So there is an isometric embedding like this. How do we prove it? We again do it one by one. Because so we start with a 1 point. So let's draw this X here. Let's find D here. Dense. Countable. Let's list it. Right. I have this dense countable space. And here is my horizon. I take the first point here, D0, and I embed. So D0. I just put it anywhere. Yeah. And then there is the next point. I can extend this isometry to isometry that maps D1 to horizon. This is the image of D1 with preserving the distance. Okay, so now I have a 2 point. I embedded 2 point. 2-point set inside. So I take the third one, is D2, I embed it somewhere here. And there is nothing stopping. You can just keep doing it. Of course, D2, there is two distances to take care of, but the definition of U guarantees it. I just keep doing it. So there is, so this way, as we produce an embedding of D with D restricted to B inside of U. This is isometry. But this one is complete, and this is dense, so it extends. And the isometry from a dense subset extends to a full space as long as the image space is complete. So extend by extend this isometry to an isometry from what they call XD to U. Using completeness. Of U. So it's universal. So we explain this word universal. Each separable metric space embeds inside. And then, okay. So then there is more to it. So I'm using, I say, the Urison universal space. So there is one. I suggest there is one, and it is indeed true. To prove proposition, let me maybe, okay, I will do one proposition. So this space is not only is universal like this, it's also highly homogeneous. So this goes hand in hand, this homogeneity with uniqueness. So, right, so I will write, so here's a U D is what they call ultra homogeneous. Meaning this, that if I have x comma x prime subset of U and x and x prime, let's say, let's call it F, an isometry, then F extends to an isometry of U. So a bijection from U to U, that is an isometry. Finite? Finite, yes, finite. Finite. Actually, one can push it to compact, but not more. It's not you can not just put here in this subspace. So with finite. And then it's this argument only done in two directions. It's a back and forth argument. So proof of that, right? Okay, have one U, there's another U, and then here two copies. Here you have this finite X. Here you have this finite X prime. You have already some bijection there. And then you just enumerate a dense subset here, a dense subset P, subset of U, just like before. En and N, dense. Here, it also is here. Dense. Or dense in U, dense subset of U. Right. And okay, so you have already a finite embedding. You look at an element of the dense, the first element of the dense set not showing up here, and then you extend it here. But then you can go back, right? You have these points, you extend. So it's an isometry now of this plus 1 point to this plus 1 point, right? And then you look at this isometry, it's a finite function. Bijection, you look at its inverse, that's also an isometry, and then you take the first element of D not showing up, first element in the enumeration not showing up among these points, the finite space with 1 point sticking out. On this finite space, an isometry to Urison is defined, so I can extend it this way. And then I flip. I go now the other direction, take the first D that's not used yet, and I go back and forth this way. And if you run this, notice that if I take this fellow here from D, its image need not be in D, right? This image will be somewhere, but it doesn't matter. So what I will, when I go back and forth, I will go over every element of D here and every element of D here. So what I will do is, by going back and forth, we get a countable dense set, or maybe two dense sets. And then isometry. Maybe called F tilde from D prime to D double prime, of course, taken with D, restricted to D and D double. Right, so I do that, and then I extend by just like before. I extend this F tilde using completeness of use. So extend F tilde by completeness of U to initially an isometric embedding. Embedding from U to U, let's say going in that direction. But because the situation is symmetric, this it has an inverse going the other way. That is also an isometric embedding. So it's actually a bijection. It's actually on which it is on. So this gives me an extension. So this is the extension. This is the extension. So we proved that each finite isometry extends to a full isometry. Fine. So this is proved. But now notice that if I had two Urison spaces, so I now want to say this actually proves uniqueness. Because if I have two different Urison spaces, U and U prime, I could put X inside of U and X prime inside of U prime, make X and X prime 1-point sets. And then the obvious isometry between the two 1-point sets, just the unique bijection, and it will extend to an isometry between U and U prime. I've never used the fact that U is equal to U prime. I just used that they both have this property from the definition. So this shows that there is an isometry between U and so now proposition universal space. This is what we will use actually. This is an important fact. This is what we will use in like Urison universal space is unique. We haven't proved it exists. So if it exists, the Urison so proof around the previous argument. With X equal to that 1 point, X prime equal to also 1 point. This included in U prime, this included in U prime, where U prime are two metric spaces, including of the Urison, the universal. And this is the argument gives isometry. So that's what we mean. It's unique in the sense any two are isometric. Any two are isometric. It's unique in the category of metric spaces with isometry. Okay. So this is so it's unique. So this is something to remember because that will get used.
So is the Urisan space a local compact?
No. It's not local. As a topological space, is homeomorphic to R to omega. This was proved. I don't remember. It's not big. So it's a non-locally compact big space. Any other questions? So it's a Polish space. Will help me look. All right. So now, all of this was from this paper, right? From Polish paper. Now we moved there some. Don't remember the names. Some ideas like this preceding this catet of construction, but now we'll do the catet of take on it. So now a construction, but it's more than that. I want to say a construction of a construction of the Urison metric space. Let me just write Urison. So Urison universal space. Okay, so this goes as follows. So this somehow we start with an arbitrary space. We'll start XD, a separable metric space. For example, a point. But we'll use it for x not equal to a point, for a bigger x. Right, so it's a separable metric space, and then we'll just pile things up on it. We'll kind of pile stuff, just put stuff in the holes and just make it more and more round and round and round, and at the end, it will turn out it's the Urison space. So we just pile stuff up on this very special space. To make it, I mean, at the end, it will just be Urison after everything is said and done. Yeah, we will make it, we'll uniformize it. All right, so here is the construction. Now, E of x, this is all f going from x to r, such that, so what are we doing is actually taking x and adding points to it in a systematic way. So we want to take x and add points to it. Each point added to x is really characterized. It's in a metric space. It will be characterized by the distances to the old points and the points, the new points that we are adding. So essentially, a new point will be a function on the old space, telling me my distance from this point is this, from this point is this, from this point is this. And then I have to tell you how to compare how to measure the distances between the new points, right? So what should it be? It should such that 1 f of x minus f of y less than or equal to d of xy less than or equal to f of x plus f of y. And 2, there exists a y. So this is essentially, if I put this would guarantee don't have the second condition. I will add all functions like that. So this will be a set of functions. The metric on the set of functions is the uniform metric, will be the supremum metric. If I just leave it like that, this will be a legitimate, it will be a new metric space, and I will know how to embed x into it. So it would be an extension of x, but it would be very much not separable. So we will add this condition that each such space has such a new function that we are adding has to be finitely supported. So there exists a y subset of x finite such that f of x is equal to infimum d of xy. Here I have d of xy plus f of y for all x in x. Right? So I have the situation, my big space x here is a function. And now I have this finite set y. And my f of x at any point is if I know the values of the function on this y, the function f is determined at any point. How do I compute its value? If this is little x, I look at the distance to an element y in y, and I look at so I want what the function is here, this, and then I look at how tall the function is at this element of y. And I go here, how tall f is here, how tall f is here. And I take all these measurements, right? So this is what I wrote here. And then I take the minimum, the infimum. And then, so this is, my f has to fulfill this condition.
Is the finite set or good?
Oh no, the final, no, x is fixed. This y depends on f. So for each f, there is a different y. Yeah. So these are different, they do depend, they do change. Was this your question?
Yes.
Yeah. Any other questions? So this is this E of x. I still have two things. I want to see x as a sub. I want to make E of x into a metric space, and I want to see x as a subspace. So first of all, metrize E of x with the uniform metric or supremum metric. D F prime is equal to supremum of x in x of x minus x. Okay. It's a metric. So we'll check. One has to check some little things like finiteness, so forth. But that's a metric. And then x with p embeds into E of x dE. Well, if I have a point here, x, I can associate with it the function, namely f, okay, point z, let's say, fz of x is the distance from x to z. And it's easy to check that this function fulfills point 1. This is triangle inequality. So fz is in E of x. And it fulfills point 1 by triangle inequality stated in two different ways. One way to state it is d of xz less than or equal d of xy plus d of yz. Another way to state it is d of xz is bigger than or equal to d of xy minus d of yz in absolute value. So this is one way of stating the triangle inequality, this first inequality. This is another way. If you just write down what one means for this function fz, it means triangle inequality. Right? You have 3 points, z, x, and y. And this is the two ways of doing it. Right? So I'll leave it to you. Check that. This is the so one is triangle inequality. In xd. Now you have to check it for xy. So this is for xyz. where Z is this fixed one, and X and Y vary. And 2, Y is equal to just this point C. It's one support. This okay. So I embedded this, and I actually view X as a subset of E of X, right? From this point on, I just think X is a subset of X. All right. So there's little bits to check, but all of it is, you just write it out. There's only one path. All right. So, fine. So this is a way of kind of adding new points, uniformizing X. And then what we do, and then another thing is E of X is separable. Again, I'll leave it to you. The separability comes from, okay, each of these is finitely supported. If I look only at functions, I fix a dense subset of X, and I only look at functions that are supported, the dense countable subset. And I only look at functions that are finitely supported with the finite support included in the dense countable set. There's only countably many such functions. Then this is the dense set. Yeah? So I will leave it to you. So E of X is separable. So we are using here this finite support. E of X separable. So this is used. All right. So this is this, and then we just keep going. Right. So this is a general notice. This is a general construction. Given a metric space, I can just apply this E and get a new metric space that contains the one that I started. All right. So now what we do is, so now fix a metric separable space. X T, and we just keep applying E to it. So I start X is my X0, then I apply E to it, that's my X1, then I apply E to X1, that's my X2, and we just keep going. So what I have is X, which is X0, is included in E in X1, included in X2, included in X3. These embeddings, I consider only this canonical embedding. There's many ways in general. There may be many ways to embed X into X1, but I consider this is this canonical isometric embedding. So this is the one that's specified there. Okay, and because all these are isometric embeddings, the function, the space X infinity, which I will just denote as the union of Xn over n, is a metric space, right? This is like the inductive limit. Yeah. Yes. Direct limit, not the direct limit. The direct limit of this space. Yeah. So if I have 2 points, in the direct limit, I want to measure the distance. They have to show up in some Xn, and I measure the distance. And if they both showed up in Xn, they keep showing up in Xn plus 1, Xn plus 2, but the distance doesn't change because the embedding was an isometry. Yeah. So this is this X infinity. This is a metric space. Metric separable space, because all of them are separable, right? I start with separable, I apply E, separable. So metric separable space. All right. So I'm not done, okay, with uniformizing. I kept adding these points, making this space look like every other space. And then, but then I'm not done. This may not be complete. So generally, won't a countable union like this. That's very dangerous for a complete space. Like normally, it's not then complete. But I will complete it. The completion. No, metric separable space with metric. Let's fix with metric. So I use D and maybe rho, right? Let's write rho. Maybe the infinity. The infinity is the completion of x d infinity. And here I will write it this way: x infinity d bar infinity is the completion of this one. Okay. And okay, so now this space, no matter the miracle here is that no matter what you started with, this x, this space is the Wilson space. Right? This is the strange thing. So lemma is the Wilson. The universal. Let's try to prove it. I just need to prove, okay, it's separable, it's complete. So the only thing I need to prove is this, that if I have a subset of it, and then another additional metric space, such finite metric space, such that all of the points of this metric space, except for one, are already in my space, I can embed this additional point. That's all I need to do. So okay, so now I have this. So okay, so now let assume I have this x1, xn. This is subset of x infinity. And then I have x1, xn, and there's some additional point x star with metric. Okay. At some point I will have to go to rho. So this is a what is this metric here? D infinity, right? D infinity bar. So with let's write it with rho or maybe D star such that, so this is a finite metric space such that D star xi xj is equal to D bar infinity xi xj. Right? So on that I just added one more point and I need to put it in. That's all. Right. So notice what I will do is this: I have these finitely many points, and I will approximate this x1 through xn very tightly with endpoints from some large xm. That's possible because this union of these xm's is dense. So there will be some large xm such that to within epsilon I can approximate these points. And I have now this x star here. So I will now I have these approximating points, and I will now, so for these approximating points, they come from some xm. So I added these functions f, I added every ideal point that with these n many points forms a metric space, I added it to the next space. So I added like a twin of this x star for the xn's, for these approximating xn's. Right? So they are, I already added these x stars to the space, and then I will just check that as I keep adding them, they are added in a coherent way, they form a Cauchy sequence, and in the limit, they give me an embedding of this x star. So that this is what will happen. Yeah? And I want to, I guess I'll check it. Let's see. So this is what we do. So what we do is now for epsilon bigger than 0, find m epsilon and x1 epsilon xm epsilon in x and epsilon. So xm now, xm's are these concrete things here, this well concrete, the ones that we fixed, such that d of, I mean by this d thing bar xi epsilon xi less than epsilon. So I approximated these points that I started with, then define f epsilon from x and epsilon to r by the formula f epsilon of x is equal to infimum dxy plus, okay, I keep this square, plus d star y x star y is x1 epsilon. So I take this formula there from point 2. So f epsilon of x, how do I compute it? I pick, so this needs to be defined here. So I go to, I have x fixed, I go to something in this approximating space, I make this, measure this distance. But once I am in this approximating space, it will correspond to something from this space. I should have written, I guess here I should have written let's write it this way. Xi epsilon xi infimum over r equal 1 to n. Now it makes sense. Right, because I'm measuring to this approximating point. I'm measuring to the approximating point, and then I'm from the appropriate subpoint, from the appropriate point in the finite metric space that I started with to x star. This is defined because d star is defined. And then this is infimum over all these i's from 1 to n. All right, so then f epsilon is in the next one, x m epsilon plus 1, which is included in x bar infinity. And then one checks, so now check that this f epsilon bigger than 0 takes some sequence convergent to 0 is coffee in x bar infinity. So it converges to some y in x bar infinity. So it converges to some, because it's a complete space. So of course, all these f epsilon, the notation is like it's a function, but it's actually an element of some of the xm's. So it's an element here. So these are all points here. So since they are Cauchy, they will converge to some y. And then, okay, so it converges some y, and then you compute d of xi y is equal to the limit as epsilon goes to infinity. Also d bar infinity, d bar infinity, xi of f epsilon. And then you just compute that this is on the other hand equal. This is directly from the definition. So d star of x star. So this number is always within epsilon of that number. Like this is just from convergence. This converges to what in X infinity. So this is simply abstract convergence in X infinity bar, right? But this is actually computable. This number here, from the definition of f epsilon, is going to be within epsilon of that number. This you can compute. So this number will be within epsilon of that number. So as epsilon goes to 0, this goes here. And then, so this is, so there's some things to check, like Cauchiness, like this computation here. But okay, that's how it goes. So this is the Urison space. And then, okay, so fine. So what do we do now with this? Okay, so what does it have to do with Polish? So let's analyze it a little bit more. One checks that this. So we continue with this development. So if I have, look at the isometry group of X with P. Now I go back now, fine. So we did something here. Now we forget about this and we go back to this group. If I have an isometry of X and I take a finitely, and I take a function from here, there is a way of moving that function according to that isometry. Namely, this function is completely determined by that formula. So what I take the isometry, I move the support y to where the isometry is moving it, and I clone the values of the function from elements on y to the moved points by the isometry, to the points that I gotten by the isometry. And then I apply this formula to clone the whole function on the whole space. So this gives me, so with phi, if I have phi here, and isometry, I can extend to isometry of E of X with PP, as I described it. So if F is supported by Y, then you write phi of F is supported by phi of Y. Let's write it phi of Y. I'm not sure. It's either phi of Y or phi minus 1 of Y, whatever works. One will give you the anti-homomorphism, the other one will give you a homomorphism. So by phi of Y and by the phi of F at X is equal to the infimum of what's this formula there, phi of XY plus F of phi minus 1 of Y. Maybe I'm correct with Y and phi of Y. Right? So this is another finite set. I use it as a support. I clone the values of F from Y to phi of Y. That's the cloning. And then I recover phi of F by applying the same formula that defines F from the original values. So that this is a canonical map from E of X to E of X. Because it's so canonical, it has to be an isometry. So we just check. One checks. We check. Okay. Extension. This is an extension. T. One has to check that's an extension. The phi acts on points of X. X is embedded into E of X in a certain way, right? Namely, the point Z goes to this function F sub Z. So one has to check that that formula actually extends, is equal to phi on the image of X, right? So I have X, so I have here X, phi goes from X to X, and then this X is embedded here to E of X. I have this extension, maybe I should call it phi star, I have this extension phi star, and I have to check that this diagram commutes. So if I have a point z here, I map it to fz, I apply this extension, I go to phi star f of z. It's the same as this should be equal to the image of phi of z. This should be equal f phi of z, yeah, with where f sub z is defined. But this is everything is canonical, so it works out. Just put in the formulas and things check out, right? So check this is an extension, and check this is an isometry of E of x. E of x would be, but again, we are in the category of isometric spaces. All these canonical things have to be isometric. But it needs to be checked. Yeah, I won't do it. And the last thing is the extension. Is a group homomorphism, a bijective group homomorphism. Again, because it's all canonical, this will check out. So I'm leaving this to you, but this is all just calculation. It's not like you have to come up with something, because there's one way, one path in the group. Just keep going, and the extension is a bijective group homomorphism, and then the image of it is closed, right? So, okay, so now, fine. So this is all algebraic. And then now I'm looking at this iso, where I lost. This iso, these are also Polish. This is a Polish group. And iso of, so what do I have here? Let's write it down. I'm here. We remember that this is so iso, what we have now, iso xd embeds into iso E of x dE, right? So this is a one-to-one homomorphism. This extension is, and then again topologies. So these groups are topological groups with pointwise convergence topology. Yes. With pointwise convergence topology. So this embedding is a homeomorphic embedding. It's a one-to-one embedding. It's a homomorphism, but it's also a homeomorphic embedding. Again, one checks that topology is everything is. So again, I will leave it to you. And so not only, so now we are, so this was Katetov up to that point with this lemma that X infinity bar is the Urson space. But now this is Uspensky's work, this observation that actually things extend. It's not just that X goes to E of X, but if I have an isometry of X, it will extend canonically to an isometry of E of X. So this observation, this is due to Uspensky. Yeah. So okay, so this we know, and this is a general observation. So I can actually do it to this whole sequence. So what I have is I have embedded. So iso x0, let me write it just without writing methods. Embeds into iso x1, embeds into iso x2. You just keep embedding. Okay, keep embedding. And everybody, all these isos, right? It's all, everybody will embed into the iso of x infinity. You just keep doing the embeddings. And so this one extends, they keep extending, you will extend to the unit. You have an isometry starting at the zeroth level. Now you extend it to x1, extend it to x2, extend it to x3, then you extend it to the union. But now we have an isometry from the union to the union. The union is a metric space. The isometry will extend to the completion, as we did many times. And also this extension is a homomorphic. So this extends to iso of x infinity bar. So I embedded my iso of x 0. This is a homomorphic one-to-one embedding from iso of x0 to iso of x infinity bar. But iso of x infinity bar, this is by cateto, iso of u of u. Because this is u. So notice what happened is I start with an arbitrary Polish space x0 here, and I should say, so all of them embed into x infinity, which then embeds into x infinity bar, which is the unison by the lemma. So I embedded this x into u, but as Uspensky noticed, actually, I embedded homomorphically, bijectively, and homeomorphically the isometry group of x0 to the isometry group of the big unison. So I have this embedding iso of x0 into iso. Well, x0, it's my x ring, right? This is what I started of u. Here also x embeds there. Great. So this is what he noticed, and then you push a little bit further. And what you see, so I said this group, maybe I'll take theorem now. We are essentially done with this proof. So theorem. Iso of u is the universal. Maybe stated it. So each Polish group is isomorphic as a topological group, not isomorphic abstractly. I don't care abstract. Topology. It's isomorphic to a closed subgroup. Of iso u. And then how do we do it? So proof. Let G left invariant. So let G be a Polish group. Let D be a left invariant metric. Not necessarily complete metric on G. This exists. No problem. Time ago. And then, okay, then what we have? I embed, note, there's a canonical embedding from G to isometry solution. Namely, map G, an element G, to the function H goes to GH. Yeah, isometry, of course, with this left invariant metric. Yeah. This is an isometry by left invariance. That this function is an isometry. So I'm mapping G to an isometry. And then I'm done. Because notice, then this maps, this is one-to-one mapping, this is the image is closed, it's a homeomorphism, it's all good. So this is topological embedding onto a closed subgroup. subgroup of iso GD, okay, then we are done, because then what we have is I embedded G into iso GD, but from this picture here, from here, this GD is some X. So it embeds from here. This embeds into a iso of this X here. And again, this is a topological homeomorphic algebraic embeddings. It preserves everything, except it's not bound. So then composition so G. Okay. Well, notice this. This is, I said, this is a homeomorphic embedding onto the image. So it's automatically its image is closed because it being a homeomorphic embedding, that's a Polish space. Well, no, okay, wait. It's not a Polish space. So in any case, you can check. You can check. Oh, okay. This is a homeomorphic embedding. That's a homeomorphic embedding. So if you go from here to here, that's a homeomorphic embedding. This is a Polish space. Because its image, homeomorphic image of a Polish space is a G delta. So its image is a G delta. But because it's a subgroup, we argued last time it's closed. So the image is actually closed. Okay. So this is a homeomorphic embedding that is group homomorphism. Group homomorphism. Right. So this homeomorphic is because it carries from here, and this is a homeomorphic. One-to-one, it's all through just because we are composing maps like this. Group homomorphism again because we are composing maps like this. So notice, so the image is closed since it's closed. The image is delta is delta. So this is a subgroup. It's closed. Okay. We are done.
How is this subtlety to subjective?
Yeah, so these are independent.
Ah.
They are not, one doesn't imply the other. So for example, so we have this kind of injective universality, and one can prove as a result of Ding that there is no subjectively universal Polish group. So there's no subjectively universal Polish, but there is an injectively universal. So they are independent. It's just two different questions, really. One does not imply the other.
Because the subjective one is more saying like by a quotient.
Yes. Yes. It's a dual. Here you have a subgroup, closed subgroup, and the other one you have the quotient. That's correct.
But then is there a universal for those TSI?
Okay, so there are universal. People look at those. So there is a universal, subjectively universal for abelian. There is an injectively universal for abelian. There is injectively universal for those. There is no subjectively universal for those. And then for TSI, there is subjective one, but I don't remember if there is an inject. I don't think so. There is no, maybe it's an open question whether there is an injectively universal one. For closed, for complete left invariant ones, there is no injectively universal. And I don't remember about whether there is a subjective universal there. Maybe that's also open.
It's the same, like
The same group.
Same paper. Yeah.
Okay.
They show there's like weekly.
Okay. So this is, I guess, this class of complete left invariant matrix is pi1 is really not a Borel class, not an analytic class. It's a co-analytic class. And if there was a universal object, it implied that the class is actually analytic, and it's not. So I guess this is both. So this TLI has none. And then, so I guess the only thing I'm in doubt of now is this TSI, whether there is a universal injective. For abelian, that's true. There is a universal injective. So these, okay, so, fine. So the fact that this is again, this is not a unique one. So Spence did a different proof earlier. For example, here you can put a homeomorphism group of the Hilbert cube. So take 0, 1 to omega. This is infinite dimensional compact space. Look at its homeomorphic group. It's also universal. The proof is it's a little more I mean, it actually can be written short. It's a shorter proof as long as you are willing to accept a big black box, right? So, but this one, this is a complete proof. Essentially, go home. I didn't check all the details, but you can just sit down and do the calculation. It's all done from scratch. Okay, so this is nice. And these universal groups like that, they do play some role. For example, when people look at equivalence relations induced by the Polish group actions, this one will give you the largest one with respect to Borel reducibility. I think I'll finish now because essentially we are done with all these examples. We are done with the universal one. And next time we'll talk about various situations where you have some form of openness of a map for free or continuity. You get continuity for free, automatic continuity or automatic openness. Say Efros is free or whatever and so forth. So this is a different subject. This is it for today. All right.
There's no Polish, there's no TSI, no CLI groups where every other CLI is a motion of a person.